All right, let's chat a little bit about alkenes and alkynes. And the first thing I can tell you is that when you have a double bond between two carbons, so let's say you have something like this, okay, a double bond between two carbons, as you see right here, that is an alkene, okay, double bond between two carbons. And when we have a triple bond, okay, between two carbons, this here, this would be an alkyne. So the first compound would be called, this would actually be called trans-2-butene, and we'll talk about the nomenclature later on. So ene for alkene, okay, and this compound would be 2-butyne, okay, ine for an alkyne. All right, so alkenes and alkynes, alkene, double bond between two carbons, alkyne, triple bond between two carbons. And so alkenes and alkynes belong to a class of hydrocarbons that we call unsaturated hydrocarbons. Remember that a hydrocarbon is just some kind of compound that is made out of two elements, carbon and hydrogen only, okay? So alkanes would be hydrocarbons, as would be cycloalkanes. But an unsaturated hydrocarbon contains one or more double or triple bonds between carbon atoms. So an alkene, like I told you, is a hydrocarbon that has one or more carbon-carbon double bonds, okay? And an alkyne, it's a hydrocarbon containing one or more carbon-carbon triple bonds. So double bond, alkene, triple bond, alkyne. And of course, you've already seen aromatics a little bit, but anyhow, aromatics are, or an aromatic hydrocarbon, is an organic compound that contains a benzene ring. And you see the benzene ring shown down here. So you notice that in the benzene ring, we have 6 carbons in a ring, but it alternates double, single, double, single, double, single, like that. Now don't confuse benzene with cyclohexane, which we saw earlier on when we looked at cycloalkanes. So if I have cyclohexane, it's got 6 carbons in a ring, okay, but there's no double bonds in it, right? So each carbon is going to have 2 hydrogens attached to it, and its molecular formula would be C6H12, unlike benzene, which has a molecular formula of C6H6. So don't get confused between those two. Again, benzene is C6H6, whereas cyclohexane would be C6H12. Anyhow, cyclohexane has nothing to do with this video because, again, we're talking about alkenes, carbon-carbon double bond, alkyne, carbon-carbon triple bond, and when we have an aromatic hydrocarbon, it contains a benzene ring where the double and single bonds alternate like this. So if you're astute, and I know you all are, you probably noticed that the generic formula for an alkene is CnH2n. Now you probably remember from earlier on that an alkane had the generic formula CnH2n plus 2. And 2n plus 2 is the maximum number of hydrogens we can have for every n number of carbons. And so you can see that alkenes are not fully saturated because they don't have the maximum number of hydrogens possible for number of carbons. So again, instead of forming a ring, though, 2 hydrogens from the generic alkane formula are replaced by a double bond. So again, what they're getting at here is that you probably remember that this formula, CnH2n, was also used for cycloalkanes, right? Because when you tethered the two ends, alkanes, when you tethered the two ends together, you lost 2 hydrogens. But again, when we make a carbon-carbon double bond, we lose 2 hydrogens as well. And the IUPAC rules for naming alkenes are similar to the ones that we saw for alkanes, with just a few modifications. So here's what we're going to do when we're naming an alkene. And I'll just put one in here. Let's say we have something like this, okay? Then we have a double bond here. Then we have, I don't know, something that looks like this. Okay, there we go. So there's an alkene that I just made up. Okay, the first thing it says is number the longest chain of carbons so that the carbon atoms joined by the double bond have the lowest numbers possible. Well, you can see that in the compound that I put here, this is obviously the longest carbon chain. And I'm going to want to start numbering from the left-hand side because I have 1, 2, 3, and 3 would be my first carbon with a double bond. Unlike if I was to number from the right-hand side, I'd have 1, 2, 3, 4. I'd have 4 as being the first carbon with a double bond. Well, 3 is a lower number than 4, and so I'm going to number that longest chain, again starting on the left, 1, 2, 3, 4, 5, 6, 7. So that tells us that this compound is some kind of 3-heptene. Okay, I'll just scribble it down here. Okay, so this is some kind of 3-heptene. Okay, and so we name that longest carbon chain that contains the double bond. The suffix of the compound is -ene. So instead of being heptane, right, it becomes 3-heptene. All right. Locate the double bond by the lower numbered carbon atom in the lower numbered carbon atom in the double bond. So again, the first place we see it is on carbon number 3, so that's why we call it 3-heptene. And there is a group attached here. It's a methyl group on carbon number 6. And so we're going to add that. We're going to say 6-methyl 3-heptene. And again, numbers and letters are separated by hyphens or dashes, and numbers are separated by commas. We don't have any of those scenarios in here. So again, this compound would be 6-methyl 3-heptene. So let's see if we can name these compounds here. Now the first one, there's only one carbon chain, and it's this one here. And you probably notice there's symmetry down the molecule like this. So it doesn't matter if I start numbering from the left or the right in this particular case, but I'll just put 1, 2, 3, 4. So this would be 2-butene. All right, and in the compound on the right, you can see that this is the longest carbon chain. It's got 4 carbons. If you had traced this out, you'd still end up with the exact same answer. It doesn't matter, so I'll just use these 4. And we're going to want to number this chain in such a way that we give the double bond the lowest possible number. Well, if I started on the left-hand side, then I would have 1, 2, 3, and my first carbon with the double bond would be 3. However, if I start numbering from the right-hand side, the first carbon with the double bond is carbon number 1. So 1 is lower than 3. So I have 1, 2, 3, 4. So this is some kind of 1-butene. All right, so 1-butene. And you can see that I have a methyl substituent at carbon number 3. So 3-methyl 1-butene. So there you go. We were able to name those compounds by following the rules. We want to find the longest carbon chain that contains the double bond. We number it in such a way to give the first carbon of the double bond the lowest possible number. We change the suffix from -ane to -ene, and then we identify our substituents. Now what if I have more than one double bond? Well, then it can get trickier to name the compounds. So multiple double bonds. It says here, some compounds contain more than one double bond. You see some examples here like carotene, which is responsible for the orange color in carrots. This compound here, 1,3-butadiene, this other compound here, 1,3-cyclohexadiene. And the nomenclature of these compounds, especially simple ones like the ones you see here on the right, is the same as for alkenes with one double bond, except if we have 2 double bonds, we would say diene. If we had 3 double bonds, we would say triene, tetraene, pentene, so on and so forth to denote the number of double bonds. So the locations of all the multiple bonds must be indicated as well within the compounds or the rings, okay? And so with the 1,3-butadiene, you can see the first carbon of the first double bond is on carbon number 1, and then the second double bond, okay, begins on carbon number 3. Same thing here. Our first double bond starts on carbon 1. Our second double bond starts on carbon number 3, like that. Now, this is something you heard me allude to at the very beginning of this section, is about cis and trans alkenes. Now, we saw cis and trans on a cycloalkane. So if you remember earlier on from a previous video, we drew a cycloalkane like this, and we said, okay, if you have 2 groups that are on the same side of the molecule, if you draw 2 wedges like this, you would call this molecule cis 1,2-dimethylcyclohexane, dimethylcyclohexane. But and we said that is one stereoisomer, and we said that if you were to change this one to down like this, right, then you would have trans 1,2-dimethylcyclohexane. Anyhow, now we can have cis-trans on a ring, but we can also have cis-trans on an alkene. And so if you take a look here at these two examples, okay, you see the carbon-carbon double bond. Both carbons of the double bond are flanked by a methyl and a proton, and on the other side we have a methyl and a proton, So what's the difference? Well, in the compound on the left, you see the two methyl groups are on the same side of the double bond, but in the other compound, they're on opposite sides of the double bond. And keep in mind, you can't rotate around a double bond, and so they're locked in these conformations. And so the one where the two methyl groups are on the same side of the carbon-carbon double bond, we call that cis, okay, for same. And then the one where the two methyl groups are on opposite sides, we call that the trans isomer. So again, like I said, alkenes have a trigonal planar geometry, right? The molecular geometry of all these carbons, this one, they're all trigonal planar, so they're all flat, compared to tetrahedral carbons that you find in an alkane. And double bonds prevent the relatively free rotation that's characteristic of carbon atoms that are bound by single bonds. So again, to repeat, if you have a carbon-carbon single bond in a linear compound, there's free rotation. However, there's no rotation here, right? You can't rotate because you have a double bond. You can make a model and prove it to yourself that you can't rotate it. As a result, alkenes can exhibit two stereoisomers, cis or trans, and we see a couple of examples here. And again, cis-trans stereoisomerism is found only in alkenes that have two different groups attached to each double bonded carbon. All right, and then it says here, in this figure, that unsaturated components in vegetable oils contain cis double bonds, which contribute to making the material a liquid at room temperature. And if you've ever wondered where trans fats come from, I won't go into much detail about it, but trans fats come from the hydrogenation or the reduction of canola oil, and when they do that, some of the cis bonds isomerize to give you trans double bonds, and so that's where we get a trans fat from. But naturally occurring fats are actually cis fats. All right, example 8.11. Cis-trans isomerism plays an essential role in many biological processes, including the response to light by the retina of the eye. Determine which of the following molecules can exhibit cis-trans isomerism and draw structural formulas to illustrate your conclusions. So if we take a look at A, you can see in A we have a CH and a CH, okay? Or you know what, let me just do it this way. I'll just put a carbon-carbon double bond maybe to make it a little simpler, okay? And I'll put a second carbon-carbon double bond like this, okay? So we have one scenario where the two chlorines are on the same side of the molecule, and then we have another scenario where the two chlorines are on opposite sides of the molecule. And so this would be a cis compound, and this would be a trans compound. And so they are stereoisomers of each other. They're both connected in the same way, in that we have chlorine, CH chlorine. But again, you can see here, the two methyl groups are on the same side of the double bond, and here they're on opposite sides of the double bond. Now in compound B, I didn't give myself a lot of room here to solve compound B, but with C, you have a carbon that has two hydrogens like this, and then this one has a chlorine and a hydrogen. Well, this is a rule that if one of the carbons has two groups on it that are identical, two hydrogens both attached to the same carbon, you can't have cis or trans, okay? There's no cis or trans in this particular case, trans, because, if you're like, well, I thought that maybe, this proton is trans with this one. Sure, but you could also say that this proton is cis with this one. And so there's no cis or trans designation that you could use for this molecule where you have two groups that are identical on one of the trigonal planar carbons. Okay, and so now we're going to turn our attention to alkynes. And like I told you, an alkyne is when we have a triple bond between two carbons. As you can see here in this molecule, this is the simplest possible alkyne we can have, which is acetylene, which is a gas at room temperature. And I'm sure some of you have used an acetylene torch to cut metal. But anyhow, the characteristic feature of alkynes, again, is that triple bond, right, between two carbon atoms. Although relatively rare, compounds containing carbon-carbon triple bonds are found in nature. For example, well, this wouldn't be a natural example, but in some birth control pills, there'll be a carbon-carbon triple bond. Anyhow, but if we want to name an alkyne, the Systematic International Union of Pure and Applied Chemistry, IUPAC naming of alkynes, is the exact same as alkenes, except we change the suffix of the parent from "ene" to "ine." Okay, so if we have, let's say, a triple bond, like in a six carbon chain, it would be heptyne, or sorry, hexyne, and then heptyne, octyne, et cetera, et cetera. Anyhow, maybe if we go through some examples, that would be better. But again, here, the simplest alkyne you can have is ethyne, and it's also known as acetylene. So these two names mean the exact same thing. Okay, so acetylene, the simplest possible alkyne we can have. All right, so let's see here. Nogestrel, a compound once found in some birth control pills. Hey, what do you know? That's what I said in the previous slide. Has a carbon-carbon triple bond. There are over 1,000 biomolecules containing carbon-carbon triple bonds, so understanding how to name them is important. Give the IUPAC name for each of the following alkynes. And so we'll start with the one on the top, and we want to number the longest carbon chain, which is this one here. We want to number it so that we give the triple bond the lowest possible number. So 1, 2, 4, 5. And so this would be 1 pent, what? 1 pentyne. Okay. It's supposed to be a letter E. Anyhow, 1 pentyne. Okay. And for the one below it, the longest carbon chain would be this one here. And again, it wouldn't matter if you chose this one, you'd still get the same answer. We'll just pick this one here. So we're going to number from this end 1, 2, 3, 4. So this is a 1-butyne, and we have a methyl at carbon 3. This is a 3-methyl. And so the name of the compound is going to be 3-methyl 1-butyne.